On November 25th, ThreeI Atlast appeared right in the middle of the solar maximum and began changing colour, in a strange sequence shifting from red to green, and then fully into blue. The gas envelope around Atlast did not spread out as a vague, fuzzy coma like a typical comet, but instead arranged itself into 7 distinct jets, some even pointing back toward the Sun before merging into a column of material nearly 1,000,000 kilometers long, while a core about 10 kilometers across remained intact, hinting at a robust internal structure with hidden conduits. This combination of strange behavior, extraordinary durability, and the fact that Atlast passed by just as humanity possesses a modern network of telescopes has turned it into an observational opportunity that may come only once in many generations. Even so, from a strategic perspective, NASA continues to focus on Apophis, Bennu and Psyche as 3 key targets, 2 bodies carrying long-term impact risk for Earth, and 1 bound up with the ambitions of resources and power. Together with ThreeI, Atlast, these 3 objects form a new triangle, in which Atlast stands as the theoretical case that forces the scientific community to rewrite physical models and reconsider how humanity understands forces structure and priorities across the entire solar system. How Atlast has already changed the course of human science is what we are about to explore next. During the solar maximum, when the Sun's magnetic field flips and eruptions lace the corona with storms of plasma, ThreeI Atlast entered the stage of observation. Its arrival coincided with the Sun's peak energy cycle, a convergence so exact that even conservative astrophysicists called it a fortunate disturbance. ThreeI Atlast did not simply pass by. It appeared at the precise moment the heliosphere pulsed at full strength, as if drawn toward the Sun's heartbeat. The alignment puzzled astronomers who noted that such timing was statistically rare, less than 1 in 1,000 orbital coincidences. Some suggested that Atlast's trajectory had been influenced by the solar wind itself, while others whispered about synchronization, an echo between an interstellar traveller and a living star. Data from coronagraphs revealed a faint halo preceding the object, shimmering as if anticipating the storm ahead. As solar flares intensified, ThreeI Atlast seemed to pause in the glare, a grain of intelligence drifting through a furnace of radiation before continuing its silent course beyond the Sun. For any comet, the moment of closest approach to a star is usually the most dramatic scene in its life. Observers expected the same spectacle when ThreeI Atlast swept toward perihelion around the Sun during this cycle. Telescopes and solar probes were queued with schedules, simulations and exposure plans built on the assumption that Atlast would erupt. Analysts modelled waves of gas-violent jets and turbulent dust, imagining that ThreeI Atlast would briefly rival classic great comets. When the first coronagraph frames came down, the Sun blazed in furious halos while Atlast appeared as a modest grain-like point. No explosive tail unfurled, no overwhelming fan of gas surged into view, only a pale signature flickering near the occulting disk. For a brief moment, some teams wondered whether ThreeI Atlast had been overestimated, a quiet visitor rather than a disruptive messenger. Yet the very restraint of Atlast during perihelion created a new tension, as if energy were being stored rather than released. Predictions were quietly revised and models were nudged to allow for delayed outgassing, asymmetric heating, and hidden jets waiting in the glare. In the calm that followed those first underwhelming images, astronomers held their breath, sensing that Atlast might be preparing a slower, stranger display. From Earth's surface, the Sun erased almost everything, a white wall of light, where no one expected to see ThreeI Atlast at all. Behind that wall, far from human eyes, coronagraphs aboard quiet satellites created an artificial eclipse hiding the solar disk to reveal the faint corona and any visitor wandering nearby. In those darkened rings around the Sun, Atlast appeared as a soft point drifting through the glow, a traveller outlined by subtraction rather than by glare. Engineers had designed the instruments to study solar storms, yet frame after frame showed ThreeI Atlast threading the boundary between streamers of plasma. Geometry said observation should be difficult with Atlast on the far side of the Sun. Still, the coronagraph masks carved out a narrow observational corridor, and within that corridor the interstellar visitor left a thin, persistent trace. Each processed frame looked almost empty at first glance, until analysts enhanced the contrast and watched. ThreeI Atlast brighten and fade like a distant heartbeat. The more they stared, the more Atlast seemed to use the corona as a curtain stepping into view only when the glare was perfectly balanced. To many astronomers, ThreeI Atlast began to feel eerily deliberate. Those hidden observations would soon reveal that the quiet speck was preparing for a far more dramatic change in brightness. The first sign that something unusual was happening came as a gentle bend in the light curve, a subtle rise where observers expected calm. Within just a few days, the recorded brightness of ThreeI Atlast had surged by roughly a factor of 400 a jump, far beyond the comfort zone of standard comet physics. Telescopes that had been configured for a modest interstellar visitor suddenly began to saturate, and exposure times, tuned for caution, proved almost useless as Atlas flooded their detectors. For comparison, even spectacular comets of the past typically brightened by a factor of 10 or perhaps 100 near perihelion, making the surge from ThreeI Atlast feel wildly disproportionate. Models that treated Atlast as a simple block of ice and dust gently heated by the sun could not reproduce the timing or the amplitude of the outburst. The onset of the brightening in ThreeI Atlast was almost step-like, as though a switch had been thrown rather than a slow diffusive release of buried volatiles. Some teams tried to explain the data by inflating the estimated venting area on Atlast, or by invoking fracturing across the surface, but the numbers still refused to align. Others wondered if ThreeI Atlast might be undergoing some deeper internal transition, a restructuring of layers or cavities that momentarily exposed an enormous reservoir of trapped material. On the monitoring screens, the brightness curve of Atlast began to resemble a vertical wall, and many late-night observers described a quiet feeling of watching something wake up. In the stillness after the initial shock, astronomers realized that ThreeI Atlast had moved from being a curious point of light to a central mystery of the solar maximum. Attention drifted away from the question of whether the data were trustworthy and settled, instead on a more unsettling thought. What would Atlast reveal next if this explosive brightening was only the opening act of its encounter with the sun? The first hint that brightness was not the only variable came from the spectrum when the glow around ThreeI Atlast shifted from a warm, dusty red toward a faint green haze. Observers had expected red tones to dominate as dust thickened near perihelion, but instead the coma of Atlast began to fill with emission lines, usually linked to more volatile gases. In the processed images, ThreeI Atlast no longer resembled a dull ember drifting through the corona. The object looked more like a lantern haloed in a soft green shell that grew night by night. Standard comet chemistry could account for green light through familiar radicals, yet the timing felt wrong, arriving suddenly after the sharp brightening rather than building gradually with solar heating. Models tuned for ordinary outgassing struggled to match both the abrupt intensity change and the swift red-to-green transformation around Atlast. Some researchers proposed that layers rich in exotic ices had been exposed all at once, while others whispered that ThreeI Atlast might host pockets of material arranged with surprising precision. On late-shift screens, the changing colour gave Atlast an oddly deliberate aura, as if the interstellar visitor were moving through a sequence of states rather than a random eruption. The more the coma glowed green, the more ThreeI Atlast felt less like a passive fragment, and more like a system responding to invisible conditions. Quietly, teams began asking whether this was only the second stage of a longer progression, a chromatic path that would continue as Atlast moved away from the sun. That question set the stage for the next surprise, when the green halo of ThreeI Atlast started to lean toward a cooler, deeper blue. Under ordinary conditions, as a comet approaches a star and its dust thickens, the reflected light drifts steadily toward redder tones. ThreeI Atlast refused to follow that script. After glowing green, the spectrum of Atlast continued sliding toward a cooler, sharper blue. For many solar system comets, increased heating means more dust, more scattering, and a gradual reddening of the coma with time. In the case of ThreeI Atlast, observers watched the opposite unfold as if Atlast were moving up an unexpected chromatic staircase. Some early interpretations suggested that ThreeI Atlast might be breaking apart, exposing ultra-fresh ices that fluoresced differently under the solar wind. Others proposed that localized jets on Atlast were sorting particles by size and composition, creating a selective filter for the outgoing light. When higher resolution images arrived after perihelion, the catastrophic breakup idea began to crumble. ThreeI Atlast emerged from its close solar passage apparently intact without the cluttered debris fields that a true disintegration would leave behind. With that scenario set aside, astronomers were left with a persistent structured colour shift that did not fit comfortable dust-driven models. The spectral path of ThreeI Atlast looked less like random boiling and more like a sequence of controlled states unfolding step by step. As data accumulated, the community quietly shifted its focus from surface chemistry to deeper mechanisms, wondering what kind of internal engine Atlast might be hiding. As the light curve and colour sequence settled into place, some teams began to read a different story in ThreeI Atlast. The timing of the brightening in Atlast, the ordered shift from red to green to blue, and the survival of the nucleus suggested a process more structured than random venting. In standard models, outgassing pushes a comet in fits and starts with jets that flicker and wander as surface patches wake and fade. In the processed frames, ThreeI Atlast appeared to sustain a coherent pattern, as if specific regions were being activated in a controlled rhythm. Measured against expected gravitational paths, the position of Atlast began to drift not wildly, but with a consistency that hinted at guidance. Instead of a cloud driven only by sunlight and chance fractures, ThreeI Atlast started to resemble a body adjusting its own trajectory within the solar furnace. That idea remained deeply speculative, yet the data encouraged some researchers to speak of an internal engine, a mechanism that could channel stored energy into directed thrust. This hypothetical system would allow Atlast to respond to changing conditions near the Sun, altering brightness, colour and motion as different modes came online. For those watching the graphs late at night, the possibility changed the mood around ThreeI Atlast from curiosity to a quiet, unsettled awe. The next phase of analysis would move beyond colour and brightness, asking whether the path of Atlast through space truly betrayed a sustained independent push. When astronomers first fit a trajectory to ThreeI Atlast, the path looked clean, a simple hyperbola, drawn almost entirely by the Sun's gravity. Then new measurements began to drift, and the plotted points of ThreeI Atlast slipped away from the predicted curve like a step to the side. Each update forced the orbit solution to bend a little more, as though Atlast were leaning against the invisible rails of gravity instead of following them. In classical comet dynamics, non-gravitational acceleration comes from jets of gas that act like random thrusters, nudging the body in flickering pulses. For ThreeI Atlast, the inferred push did not look random at all. The change in motion unfolded smoothly with a direction and amplitude that held steady over many observing windows. The effect grew strongest near perihelion, just when the internal engine hypothesis for Atlast had begun to circulate in late-night discussions. To keep matching the sky models, had to add a sustained sunward or anti-sunward thrust term, as if ThreeI Atlast were choosing how hard to press against the solar field. Plotting the corrected orbit, analysts saw the observations tighten while the required non-gravitational terms swelled to values rarely assigned to any known comet. The more carefully they checked for simple errors, the more firmly ThreeI Atlast insisted on its altered course, crossing out comfortable assumptions with each pass. In the dim glow of monitoring rooms, the numbers gained an emotional weight of their own, a hint that Atlast might not be a passive passenger in the heliosphere. That realization set the stage for deeper comparisons, inviting the next round of analysis to measure just how extreme the velocity of ThreeI Atlast had become. When the raw velocity numbers first appeared on the screen, ThreeI Atlast looked less like a comet and more like an arrow. Near perihelion, ThreeI Atlast raced through the inner system faster than many catalogued long-period comets that had decades to fall inward. Typical bodies of this kind skim the Sun at high, but predictable speeds, their motion set almost entirely by gravity and modest jets. Against those benchmarks, ThreeI Atlast pushed the curve, brushing past escape velocity margins with a comfort that made orbitalists uneasy. Early comparisons to the interstellar visitor Borisov showed ThreeI Atlast carrying a significantly larger non-gravitational component in the final velocity budget. Where other comets picked up a slight extra push from outgassing, ThreeI Atlast seemed to gain a whole new gear near the Sun. Graphs that overlaid classic great comets with the track of ThreeI Atlast turned into a quiet shock exercise for graduate students. The historical lines rose smoothly, while the line for ThreeI Atlast bent away like a diver, leaving a platform earlier than expected. Some analysts tried to rescue a natural picture by boosting venting rates or tweaking bulk density, but the fits snapped under scrutiny. The more parameters they adjusted, the more ThreeI Atlast demanded yet another correction, as though the visitor were shrugging off each simple explanation. In late-night control rooms, the velocity plots began to feel less like inert math and more like the handwriting of ThreeI Atlast itself. Observers spoke softly of chasing a moving target that always stayed one step ahead, a traveller that knew how fast to run. That sense of intention did not prove anything, yet the speed of ThreeI Atlast turned attention toward the structure of the surrounding gas. The next question was whether the pattern of jets around ThreeI Atlast could possibly account for such a sustained rule-breaking sprint through the Sun's domain. When the glare around the nucleus sharpened, observers noticed something uncanny in the halo that wrapped around ThreeI Atlast. Instead of a smooth, fuzzy coma, the glow around Atlast broke into distinct rays, 7 narrow plumes fanning away like the spokes of a wheel. High-contrast processing confirmed that each beam from ThreeI Atlast held a clean edge, as though gas were being channeled through specific nozzles. Typical comets shed material in ragged overlapping fans, but the pattern around Atlast looked geometric, almost architectural. Measurements showed that not all of the plumes from ThreeI Atlast were pointing away from the Sun. One group of jets appeared to lean sideways, while at least one major ray seemed to bite back toward the solar glare. In standard dust and ice physics, solar radiation and wind push material away, sculpting tails that always stream broadly anti-sunward. Seeing a structured set of beams around ThreeI Atlast, including a component with a sunward tendency, forced models into uncomfortable corners. Some teams suggested that uneven topography on Atlast could focus the outflow into channels like air forced between mountain ridges. Others tried to invoke complex magnetic coupling, imagining ThreeI Atlast as a charged body threading invisible field lines around the Sun. Even with generous assumptions, the clean separations between the 7 plumes of Atlast were hard to reproduce in simulations. Random venting wanted to smear everything into a blur, yet the visitor kept sketching the same sharp pattern, frame after frame. In the quiet of analysis rooms, astronomers watched time-lapse sequences where ThreeI Atlast spun slowly, while the 7-fold structure pulsed but refused to dissolve. The scene felt less like melting rock and more like a system adjusting valves, rebalancing thrust in response to solar pressure. That impression, still unproven, but emotionally persistent, prepared minds for the next escalation. Within days, the 7 rays surrounding ThreeI Atlast would begin to merge, giving birth to an even larger, stranger reverse-directed plume. At first, the 7 narrow plumes only flickered and flexed like a halo of separate engines around ThreeI Atlast. Then, over a sequence of frames, the rays began to draw together, until the glow around Atlast thickened into a single towering column. In enhanced imagery, that column from ThreeI Atlast stretched for nearly 1 million kilometers, a bright shaft cutting through the solar wind. The merged plume did not behave like a loose fan of dust. The structure held its shape as Atlast rotated, as though a great searchlight were anchored to the nucleus. Analysts traced the orientation of the new feature and realized that the main column did not simply stream away from the Sun. The geometry around ThreeI Atlast revealed a second, fainter structure angling back toward the inner glare, a reverse-directed flow that defied classroom sketches of comet tails. Models that treated ThreeI Atlast as a porous snowball could not easily generate a stable sunward component without tearing the nucleus apart. Even aggressive simulations with vents erupting in random bursts wanted to smear the plume into arcs and fans rather than a disciplined spear. Some teams suggested that complex interactions between the solar wind and charged grains around ThreeI Atlast might be routing material along twisted magnetic lines. Others quietly tested scenarios in which the nucleus of Atlast hosted organized channels plumbing that could re-aim outflow to counter external forces. In time-lapse sequences, the grand column behind ThreeI Atlast flared, thinned and brightened again, but the overall architecture refused to dissolve into chaos. The scene felt less like a natural firestorm and more like a controlled burn, a structure answering pressure with counter-moves. For late-night observers, the sight of a million-kilometer plume hanging behind ThreeI Atlast carried an eerie calm, like a ship leaving a deliberate wake. The question that followed was unavoidable. How strong must the core of Atlast be to endure such violent exhaust without breaking apart, and what did that resilience say about the visitor's true nature? Estimates of the nucleus suggested that ThreeI Atlast was no fragile snowball, but a block of rock and ice roughly 10 kilometers across. For most objects of that size, repeated heating, cracking and outgassing near a star would gradually carve deep wounds into the surface, leaving scars and fragments in their wake. ThreeI Atlast, by contrast, appeared to endure the solar encounter with a kind of stubborn integrity, shedding immense plumes, while the core remained stubbornly coherent. From a structural standpoint, the stress on ThreeI Atlast should have been immense. The visitor had likely drifted through interstellar space for billions of years, colliding with dust-charged particles and the subtle tides of distant stars before falling into the Sun's grip. Every kilometer travelled increased the odds of damage, yet ThreeI Atlast arrived in the inner system, still capable of venting material in disciplined towering beams, Some researchers argued that only an unusually dense monolithic body could give ThreeI Atlast such resilience, a kind of cosmic boulder hardened by age and pressure. Others suggested that Atlast might be layered with an internal lattice, or honeycomb that distributed stress more efficiently than a simple solid core. In those models, the pathways that guided gas outward from ThreeI Atlast could also act as trusses, allowing the nucleus to survive violent exhaust without crumbling. The more simulations tried to break ThreeI Atlast apart, the more assumptions they had to bend to keep the nucleus intact. In quiet offices, the endurance of Atlast began to feel like an additional clue rather than a background detail, an engineering note hidden in plain sight. That sense of overbuilt strength would feed directly into the next question. How improbable was it for a body like ThreeI Atlast to survive both the interstellar journey and the solar encounter, and what did that improbability say about the true rarity of the visitor? For many astronomers, the appearance of ThreeI Atlast in this decade felt like a lottery win. Across billions of years, the arrival of Atlast came in the first age when humans could watch with such precision. Space telescopes, heliophysics missions, and deep surveys were all awake at once, giving ThreeI Atlast more eyes than any earlier interstellar visitor. The odds that a body of this size, speed, and resilience would pass the inner system just as our instruments matured seemed vanishingly small. When researchers folded in estimates of interstellar traffic, the path of Atlast began to look like a 1 in a million alignment of timing and technology. ThreeI Atlast had survived a journey through galactic space, slipped into the Sun's domain, and done so at the precise moment humanity could trace every flicker. For observers on night shift watching ThreeI Atlast evolve in real time, felt like standing at a window briefly cut into the fabric of cosmic history. The changing signature of Atlast illuminated questions about comet physics, planetary formation, and even the possibility of engineered structures that might ride on stellar winds. As the orbit carried ThreeI Atlast toward its December approach to Earth, astronomers knew that each night of tracking added lines to a record that would not repeat. That awareness gave the graphs and spectra a hushed gravity, as if Atlast were offering a single lesson, before slipping back into the dark between stars. The next chapter would have to ask why agencies such as NASA, faced with such a rare teacher, were already weighing Atlast against nearer and more practical threats. As predictions sharpened, astronomers traced the future path of ThreeI Atlast like an engraving in space. In refined ephemerides, Atlast swept through perihelion, then arced outward toward a December encounter that would carry ThreeI Atlast closest to Earth before it slipped away. Those calculations turned the days around closest approach into a narrow observational window, a moving corridor that Atlast would cross only once. To exploit that corridor, telescopes were scheduled so that ThreeI Atlast could be followed across hemispheres. Mission planners mapped when Atlast would stand highest, when the moon would interfere least, and when radio arrays could listen for changes in outgassing. Against this tuned schedule, ThreeI Atlast looked less like a random streak and more like a train arriving on an unrepeatable timetable. The knowledge that Atlast would never return gave every predicted coordinate weight an invitation to look deeper before ThreeI Atlast vanished into interstellar night. While ThreeI Atlast drew headlines as the mysterious interstellar visitor mission planners at NASA were studying a different list. On internal charts, the top priorities were 3 massive targets inside the solar system: Apophis, Bennu, and Psyche. Apophis carried the drama of a near-Earth passage only tens of thousands of kilometers above the surface. Bennu came with a measurable impact probability in the next century, a slow-moving dice roll that agencies could not ignore. Psyche promised a laboratory inside a metallic core, a chance to see the heart of a shattered world. Against these stakes, Atlast looked to NASA less like a threat and more like a fleeting teacher. Atlast inspired curiosity, but Apophis, Bennu, and Psyche demanded hardware budgets and long-term strategies. For observers following ThreeI Atlast, that contrast felt unsettling, and it naturally led toward a closer look at Apophis first. While the public watched ThreeI Atlast drifting through solar light mission briefings kept returning to another name, Apophis. Compared with the distant enigma of Atlast, this near-Earth asteroid carried the weight of a scheduled encounter, a date already circled on every planetary defense calendar. On an April evening in 2029, Apophis is expected to sweep closer to Earth than many high-orbit satellites, passing at a distance of only a few tens of thousands of kilometers. For ThreeI, Atlast the Sun was a stage seen from afar, but Apophis will cross a corridor where city lights and human radio noise rise straight up to meet it. Simulations show that Earth's gravity will tug hard on Apophis, twisting its path in ways that are exquisitely sensitive to its internal structure and rotation. Each new radar echo refines the numbers, yet the post-encounter orbit of Apophis still carries a shadow of uncertainty that ThreeI Atlast never imposed on our home planet. In risk maps, Apophis sits not as a cosmic curiosity, but as a practical test of whether humanity understands how to follow and model a close passage. The contrast with ThreeI Atlast is sharp. Atlast invites questions about distant engineering and interstellar journeys, while Apophis demands accurate millimeter-scale predictions in our own neighbourhood. For researchers, that difference breeds a quieter kind of tension, the feeling that this god of disorder is a stone we cannot afford to misread. As the date of closest approach approaches, ThreeI Atlast fades toward the edge of attention, and the spotlight turns inward toward the rock that will brush past our sky. The next logical step in this story is to ask how far space agencies are willing to go in hardware and manoeuvring to greet Apophis when it arrives. Long before Apophis dominated the risk charts, a quiet spacecraft was already rewriting the map of small bodies. That vehicle would later be renamed OSIRIS-AX, and its new trajectory would cross paths with Apophis, just as interest in ThreeI Atlast reached its peak. Originally, OSIRIS-REx had circled Bennu-collected samples and learned how fragile rubble piles really behave under sunlight and subtle thrust. Those lessons framed the way scientists interpreted the delicate non-gravitational pushes acting on ThreeI Atlast, even though Atlast never carried a visiting probe of its own. When mission planners realized that OSIRIS-REx could be retargeted, engines were fired to send the spacecraft toward Apophis, instead of letting it drift into retirement. The scale of the maneuver showed how seriously agencies treated a single encounter, a level of investment that ThreeI Atlast, for all its mystery, never received. Diagrams in mission control showed the reused craft threading through space to meet Apophis at close range, ready to watch how tides and torques reshape a near-Earth asteroid. In presentations, the same charts often appeared beside plots of ThreeI Atlast, a visual reminder that theory about Atlast depended on distant light, while Apophis would get a direct escort. That contrast lent a bittersweet tone to each new observation of ThreeI Atlast, as if the interstellar visitor were giving a masterclass from the balcony, while the main cameras pointed at the stage below. The redirection of OSIRIS-AX underscored where concrete priorities lay, and it quietly prepared the narrative to turn from immediate danger to deeper time. The next focus would shift towards Psyche, a metallic relic whose story might illuminate the ancient interiors that objects like Apophis, and even ThreeI Atlast only hint at from afar. For mission planners, Psyche feels like the exposed heart of a world that failed to finish forming. Radar and spectral studies show that Psyche reflects like metal, suggesting a core rich in iron and nickel, where rockier planets would hide such layers deep beneath crust and mantle. Unlike ThreeI Atlast, which brushes through the solar system as a visitor, Psyche circles the Sun as a long-term resident, quietly carrying a record of early planetary violence. Density estimates and brightness patterns hint that Psyche may be the stripped interior of a shattered protoplanet, a core left bare after colossal collisions. Where ThreeI Atlast tempts researchers with questions about engineered thrust Psyche, offers the chance to study the natural machinery of differentiation, the way young worlds separate metal from stone. A dedicated spacecraft will map Psyche's gravity composition and magnetic history, turning the asteroid into a laboratory for the physics that once shaped larger planets. To many scientists, Psyche resembles a frozen cross-section of worlds like Earth, a place where metal once flowed and fields once wrapped a surface in invisible lines. Seen beside the data from ThreeI Atlast, Psyche anchors speculation about internal structure, suggesting how cavities, lattices, or conduits might form inside dense bodies. If a visitor like ThreeI Atlast truly hides channels for focused outgassing, or thrust Psyche may show how such pathways could arise in nature before any engineering ever occurs. That possibility lends a quiet emotional weight to every new image of Psyche, as if the metallic relic were offering context for the stranger behaviour of Atlast. In the narrative of risk and reward, Psyche therefore stands at a crossroads, bridging pure scientific curiosity and the more controversial question of how much metal such a core may actually hold. As mission profiles for Psyche solidified, economists began attaching price tags to the metal they believed lay within. Compared with that hypothetical treasure, ThreeI Atlast looked like a poor visitor carrying information and unease instead of commodities. Some bold estimates claimed Psyche could flood human markets with more iron and nickel than Earth has mined in all recorded history. In the shadows of those numbers, Atlast became a reference point, a reminder that not every influential object can be measured in currency. Whispers grew that if Psyche truly holds concentrated precious metals, long-term extraction plans might already be discussed in closed unrecorded rooms. In that scenario, confirming or downplaying key measurements would be as politically sensitive as admitting how little we understand ThreeI Atlast's internal workings. The result is a tension where one world tempts greed while Atlast tempts imagination, and both encourage selective transparency from institutions. That tension naturally prepares the listener to look next at Bennu, where value is calculated not in metal, but in probabilities of impact. Among all the rocks that cross Earth's orbit, Bennu holds a special place on NASA's watch list. Where ThreeI Atlast brushes the solar system once and disappears, Bennu keeps returning its orbit, weaving through our neighbourhood. Decades of tracking have given Bennu an impact probability around the year 2182, a number small in daily life but serious on planetary timescales. By contrast, ThreeI Atlast never acquires such a date on the calendar. Atlast disturbs models more than it threatens cities. Radar echoes and optical campaigns have mapped Bennu as a loose rubble pile, a body that can subtly change its path under uneven heating. This sensitivity to the Yarkovsky effect means Bennu's future track can drift as sunlight pushes at different facets, a process ThreeI Atlast helped visualize by exaggerating non-gravitational forces in a dramatic regime. Every refinement of Bennu's orbit narrows the cone of possible futures, yet a sliver of risk remains a line analysts cannot erase. In that light, Atlast becomes the distant theorist, and Bennu the practical exam, a pairing that steers the story toward how agencies juggle curiosity, fear, and resources. The Yarkovsky effect is a gentle, invisible thrust, born from sunlight warming a rotating body. For Bennu, and in a more dramatic regime for ThreeI Atlast, this subtle push acts like a constant, uneven hand on the orbit. As surface patches heat and cool, they re-radiate energy, turning Bennu into a slow, tumbling engine that slightly rewrites its own path. ThreeI Atlast exaggerated this behaviour, showing how non-gravitational forces can bend expectations when outgassing or structure amplify the same principle. In long-term simulations, tiny Yarkovsky nudges accumulate into kilometres, then thousands of kilometres of drift-stretching prediction envelopes in uncomfortable ways. The more precisely analysts try to pin Bennu down, the more the Yarkovsky term reminds them that certainty is always provisional. In this light, ThreeI Atlast becomes a distant, overclocked demonstration, while Bennu remains the local test case whose uncertainty cone actually crosses Earth's future. That pairing sets the tone for quiet unease, and leads naturally to the question of how much of Bennu's risk story is being fully shared. In public briefings, Bennu often appears as a managed problem framed with calm probabilities and long timelines, while ThreeI Atlast carries the mystery. Behind closed doors, some independent analysts suspect that the risk story for Bennu is delivered with a deliberate softness, and Atlast becomes the comparison point. Models show how small changes in surface properties can swing Bennu's future path, yet only curated summaries usually reach headlines. ThreeI Atlast, by contrast, exposed non-gravitational chaos in full view, forcing discussions about unseen forces that planners rarely enjoy having. To those watching from the outside, Bennu sometimes feels like a dossier with redacted lines, whereas ThreeI Atlast feels like an unedited log. The notion emerges that agencies might choose which uncertainties to amplify and which to let fade depending on consequences for policy markets and public mood. In that narrative, Bennu becomes the quiet file in the drawer, and ThreeI Atlast becomes the noisy case study used to explore theory at a safer distance. The selective emphasis does not prove any concealment, yet the contrast keeps raising questions. Why should an interstellar visitor such as ThreeI Atlast reveal every awkward parameter in public plots, while a local neighbour like Bennu receives gentler framing? That asymmetry of tone feeds a slow, uneasy curiosity, one that prepares the mind for a broader look at how all three major targets, and ThreeI Atlast together, define a new era of planetary awareness. On risk charts, planners sometimes imagine a triangle whose corners are Apophis, Bennu, Psyche, and the interstellar visitor, ThreeI Atlast. Apophis carries the sharp near-term threat of a close pass, Bennu holds the slow probability of impact, and Psyche hides the power to disturb entire markets. Within that triangle, Atlast occupies a stranger role, representing not direct collision danger, but a challenge to our understanding of forces and structure. Where Apophis and Bennu demand trajectories to protect Earth, Atlast demands models that can explain controlled looking thrust and colour shifts. In practical terms, Apophis is the emergency drill, Bennu is the actuarial table, and Psyche is the speculative balance sheet, while Atlast is the theoretical exam that keeps rewriting the questions. For scientists who follow Atlast, this 3+1 arrangement feels uneasy, as though the most enigmatic point on the triangle hovers just off the plane of simple risk. The more data arrive, the clearer it becomes that Atlast stretches mental frameworks, while the other three stretch engineering and policy budgets. That asymmetry gives Atlast a quiet gravity in the story, a reminder that not all danger is measured in impact energy or metal tonnage. Together, Apophis, Bennu, Psyche, and ThreeI Atlast define a new landscape where curiosity and survival are tangled. The next step is to ask how agencies translate that tangle into concrete priorities, and how Atlast fares when budgets and missions are finally assigned. Budget charts tell a quieter story than headlines, a story in which ThreeI Atlast rarely appears on the first line. When agencies lay out columns of numbers, the largest blocks of funding flow toward missions that visit Apophis, Bennu, and Psyche, while Atlast remains in the category of remote observation. Dedicated spacecraft, retargeted probes, and new instruments are assigned to near-Earth asteroids that might someday threaten cities or unlock metallic cores. ThreeI Atlast, despite reshaping models of non-gravitational forces, is followed by telescopes and survey programs that already exist, borrowed time on shared platforms. From a strategic point of view, that choice is defensible. Apophis demands preparation for a close flyby, Bennu requires constant tracking, and Psyche promises insight into planetary interiors and resources, while Atlast simply passes through once. On planning slides, ThreeI Atlast becomes a column labelled Opportunity Science, important, but not mission driving a teacher rather than a patient. For scientists who have watched the strange jets and colour shifts of ThreeI Atlast, that ranking can feel uncomfortable. Atlast challenges basic assumptions about structure and thrust, yet receives no purpose-built probe. No last-minute trajectory changes the way Apophis earns from Osiris AX. The imbalance raises a subtle emotional question. What does it mean when a visitor like ThreeI Atlast can shake theoretical foundations without triggering the same level of hardware response? As that question lingers in the background, the narrative naturally pivots toward the clearest single test of planetary defense, the coming close passage of Apophis, that will act as a live-fire exercise for everything learned so far. In planning rooms, Apophis often appears as the final boss of the near future, while ThreeI Atlast lingers as the enigmatic tutor in the background. Apophis will not glide past at a comfortable distance the way Atlast does, but will dive inside the orbit of many satellites, forcing every model to prove its worth. For planetary defense teams, the 2029 flyby is a live examination, where no rehearsal can fully mimic the real event, and ThreeI Atlast becomes the theoretical chapter that must already be understood before the exam begins. As Apophis swings by, Earth's gravity will twist its trajectory, revealing how mass is distributed within the asteroid, just as Atlast revealed how non-gravitational forces can warp an interstellar path. High-powered radar optical arrays and spacecraft like Osiris AX will watch Apophis from multiple vantage points, applying lessons first hinted at by the behaviour of ThreeI Atlast. Where Atlast invited speculation about internal channels and engineered thrust, Apophis will show how a real hazardous neighbour responds to tides, torques, and perhaps subtle surface changes. In one sense, Apophis is the crash test, and ThreeI Atlast is the strange design sketch pinned to the lab wall, a pairing that shapes how fear and curiosity are allocated. The closer the date draws, the more Apophis absorbs attention that once belonged to Atlast, yet the fingerprints of Atlast remain on the equations guiding that focus. If the passage of Apophis unfolds smoothly, confidence in our models will grow, and the ghost of ThreeI Atlast will seem more like an early warning. If unexpected behaviour appears, planners may be forced to admit that the strangeness first seen in Atlast was not an isolated quirk, but an omen of how complex even local space can be. In economic forecasts, Psyche is often framed not as a scientific target, but as a vault, a potential stockpile of off-world metal that could dwarf terrestrial reserves. If even conservative estimates hold the iron and nickel inside Psyche could destabilise commodity markets, while ThreeI Atlast, by contrast, offers only disruptive ideas rather than awe. That imbalance tempts a different kind of control, the quiet urge to treat Psyche as a strategic asset rather than a neutral laboratory. Policy papers speculate about future mining consortia and exclusive rights, hinting that data on composition and purity might someday be guarded as tightly as any classified file. In that imagined future, Whoever understands Psyche first could shape the rules of off-world industry, while the lessons from 3I Atlast shape the models that guide such ventures. 3I Atlast reminds planners that non-gravitational forces and internal structure can surprise even the best simulations, a warning that any extraction fleet near Psyche would be gambling with incomplete physics. Some observers worry that this mix of enormous value and incomplete understanding encourages selective disclosure, where only certain spectra and gravity maps are highlighted for the public. In that scenario, 3I Atlast becomes the ghost in the narrative The Visitor that showed how much can be hidden behind apparently simple light curves. The emotional tone around Psyche is therefore different from the awe that surrounds 3I Atlast. Where Atlast evokes wonder and unease, Psyche stirs ambition and caution, a sense that the next phase of exploration could quietly define who controls the solar system's raw materials. That realization leads naturally to a final comparison. If Apophis tests planetary defense and Bennu tests long-term risk Psyche, and 3I Atlast together test how honestly humanity can face the twin temptations of knowledge and power. In public imagination, 3I Atlast shines as the headline wanderer between stars. In internal planning tables, Atlast appears farther down, a guest folded into existing observation programs. While probes are redirected for Apophis, and bespoke missions are built for Bennu and Psyche, Atlast is assigned borrowed telescope time and shared survey slots. To many researchers, that minimal hardware commitment makes Atlast feel like a passing tourist, rather than a primary concern. Yet the strange jet's colour shifts and non-gravitational pushes from Atlast keep echoing through models that guide those very missions. In that quiet imbalance, Atlast becomes the overlooked narrator of a story whose main actors are still gathering on the stage near Earth. In the long view, 3I Atlast may be remembered less for danger than for the questions it forced open. Apophis, Bennu and Psyche reshape strategy and industry, while Atlast quietly reshapes what physics must explain. If humanity listens carefully, 3I Atlast could mark the first whisper of a new cosmic era,